Hey guys, welcome back to CMTEQ channel. In this tutorial, we're going to discuss the rating of this circuit breaker in connection to a fault current calculations. Now, when determining what is the rating of the circuit breaker, you have to ensure that... Whoa, what just happened? I think there is a power outage. Okay, we're going to... Okay, so how to build an electronic main sensing. Basically a device that can detect a power outage and automatically launch in a backup system. Obviously, this is similar to what we call a switch over circuit or a changeover circuit. Now, let's go ahead and find out what we can do with that. So I'm going to stop this tutorial and move on to do that. Okay, so here we are to design our main sensing circuit. So we are connected straight from our mains. Okay, so we got a live and we have a neutral. Now remember, this is AC, so it could be either 120 volt or 230 volt depending on where you are. So we got live and neutral. Now we can include a fuse here for safety. Okay, so we include a fuse for safety. That is very important. And what's the next thing to connect? We're going to connect our capacitor. I forgot to mention that there are several circuits that you can design for main sensing circuit. Most of them are used with inverters. They called changeover switches, where it can automatically detect when there is a power outage and then it switch over to the backup system. Now this one here, we're going to be using the simplest voltage regulator from the mains, which is a capacitor dropper circuit. So we're going to include our capacitor here. Now the capacitor dropper circuit is basically we're using the capacitive reactance XC, okay, to limit the current without wasting power in the form of heat. Okay, otherwise we'll just put a resistor to limit the AC current here, but there's going to be a lot of heat. So which means in this case here, we use XC, which is the impedance of the capacitor, the capacitive reactance, and that's going to limit our current. Now, remember this capacitor here need to be a 400 volt capacitor, okay? Now the value of the capacitor will determine how much current will go into our load circuit that we want to have on this side, okay? Now, remember also, because this capacitor is connected to your live and neutral, it's going to be fully charged either on 120 or 230. So that means if it's not discharged, you disconnect AC, there's still going to be a 120 or 230 volt here. Now to avoid someone getting shocked, you connect two resistors here just to enable it to discharge the capacitor. Now the value could be 500k each. Make sure that it's big resistor so that it discharges it faster. Okay, so we've got our circuit like that. Okay, now to complete our circuit, on the other end of the capacitor dropper connection here, we put a bridge rectifier. Okay, I'm just going to represent a bridge rectifier with a diode symbol. We know that it's a full wave bridge rectifier, okay, with 4 diodes connected to rectify the AC signal. So which means here we got a plus and we got a minus. Okay, so what's happening here? We fully rectify our AC, and the current going through this bridge here is limited by the capacitive reactance of this big capacitor here. Okay, now let's say we put a 220 nanofarad capacitor here. We know that we're going to be limited by the current here. We're going to calculate that later. Okay, so what's happening here now, we can then configure from the output here. So let's say we want to smooth the DC voltage that's coming here, because we know that it is a ripple DC voltage that comes out of here, full wave. So the capacitor will just smoothen it and reduce the ripple. And we go, the next thing is we connect the Zener diode. Okay, now I'm going to put a 5 volt Zener diode here because the circuit that I want to power here is going to be a 5 volt circuit. What's the next thing I'm going to connect? I will connect a resistor here. I connect a 1k resistor here. Now, many of you might be asking, why is there no resistor here to limit the current going into the Zener diode? Because basically, there could be an inrush current here once you connect AC, because the capacitor will try to pull as much current on the first time constant, and all of that current will come through here, okay? Also, based on this capacitor here, the Zener diode might break if it's not rated higher. But for design sake, we can put a resistor, but I'm leaving it out here. So the only current limiting for this one here is for the XC, that is limiting, the capacitive reactance is limiting the current through the Zener here. Otherwise, there is no protection for the inrush current. We can include a resistor here, okay, that can also limit the inrush current. Okay, now the next thing here is to connect our isolator, okay, an optocoupler. I forgot to mention that this circuit is actually an isolated MEMS sensing circuit. So we're going to connect an opto isolator here. And once again, I'm just going to build it as a block. And we know that an opto isolator is a device that got a diode or an LED inside of it that is connected like this. Okay, a light emitting diode. Okay, so this one here is a light emitting diode, and when there is conductivity, this diode illuminate inside, it bias the transistor here. Okay, there is a transistor connected there. Okay, it's an NPN transistor that's connected this way. Okay, so this is the collector and this is the emitter. Now this 1K resistor is precisely for this LED inside a opto isolator. This could be any opto isolator that you can find. Now I'm using a KB817, which is a very popular one. Okay, now what am I going to do here? On this side here, I'm going to connect a relay. I'm going to connect a relay switching circuit so that now I know that this transistor is only going to conduct when there is a presence of MEMS here. When there is a presence of MEMS here, okay, there will be a 5 volt here, and the 5 volt is going to set up a current, okay, that's going to bias this LED, drive this LED, and in turn it's going to switch on this transistor inside the opto isolator. Now what I'm going to do is I'm going to then include another transistor into the circuit that's going to switch our relay coil. So let's go ahead and plug in a transistor here. So we've got another NPN transistor that's going to be connected like this. Okay, and on this side here we're going to have a relay. So this is our relay coil. Okay, that's a relay coil. Now the relay here is going to be switching. So we're going to have 2-pole relay, a normally closed and a normally connected. Okay, so now let's say here we got our input pole, and then we got 2 poles here. So this side, the relay is on a normally closed. In our case here, we are connecting a 12 volt supply here, plus 12 volt. So let's say it's coming from the battery. So we've got a 12 volt battery there. Okay, so what will happen here is, from the relay here, we need to have an output that is coming straight from the 12 volt and is going into our lamp. Now let's say we've got a lamp here. I'm just going to put a symbol of a lamp like that. And this is going to ground. Okay, and this ground here is basically the same ground as this one on the transistor. Now you can see that this circuit is completely isolated from our MEMS reference here, because this one now is reference from our 12 volt battery. Okay, now so this is a plus and this is a minus from our 12 volt battery. Okay, now the same 12 volt is connected, and that's the one that is powering the relay and also the collector of this transistor here inside the opto isolator, okay, the optocoupler. So what will happen when there is MEMS? Okay, MEMS is present, the LEDs is on, the transistor here is biased, so we've got conductivity, so current will flow like this, okay, and that in turn will induce some current here, and then we put a resistor here to the base of this transistor. So we're going to bias this transistor here. So we can put, I don't know, a 470 ohm resistor, it doesn't matter, 470 ohm resistor. We can calculate how much current we set for this transistor here. That will basically mean the circuit is completed. When this transistor is biased, okay, we're going to have a flow here, and what will happen is the relay here, the relay coil will be energized. The relay coil will be energized, and that will cause this pole here to switch over to this side, cutting power from this one. Okay, so if there is no AC, basically this transistor is off and this transistor is also off. The relay is not energized and this lamp is going to stay on. Okay, because it is connected on a normally closed path of the 12-volt battery. And we just need to include here a diode to protect here. Because after the relay have been energized, there's going to be a back EMF here. Now, if we don't want to be changing transistor all the time, we better include the diode here to block the back EMF. So this is basically the circuit for an isolated MEMS sensing circuit in a simplest of the form. So what will happen, I've already explained it, I will go one more time. In the presence of AC, this capacitor, the cap dropper, will charge and will release some current through the bridge rectifier, and that current will also charge this smoothing capacitor here, and we're going to have our 5-volt regulated here, and that in turn is going to induce current to bias this LED inside the optocoupler, and that in turn will bias this base here, and this transistor will turn on, and there will be some current that will flow from the battery independent of the MEMS, and that current will then bias this transistor here. And what will happen when this transistor is on, there will be some current that's going to flow from the coil down this way, and when the coil is energized, this switch will flip this side, and that will cut power from here. So which means if there is AC, this one is going to be off. Okay, if there is MEMS, this one is off. When MEMS goes away, this one comes back on. So automatically MEMS sensing. So what would mean is you need to have a parallel circuit. So you've got your main connected circuit, and then you've got your backup connected circuit. So both circuits cannot be connected on the same MEMS. So the two lamps must be disconnected. So you've got one lamp here, okay, one lamp here running on the main, and one lamp here running on your backup. That way when your MEMS runs out, okay, when there is power outage, you've already got a backup that will come on this side. So this is how the circuit works. Now we need to do another calculation, and that will be how to calculate this current that's going on here. I've already said in the beginning that this current is limited by your XC, which is your capacitive reactance. Now it's very simple to calculate that. Now if you have been studying engineering, electrical or electronics, we know that XC, okay, is given by, that's a capacitive reactance, okay, the impedance of the capacitor is given by 1 over 2 pi, okay, FC, okay. So F is the frequency of your MEMS and C is your capacitor. Now in this case, we're just going to replace here quickly so that we can get our XC. So we got our 1, okay, 2 pi. Our F here, I'm going to take a case of 50 Hertz, okay. For those using a 230, for those on a 120, that will be 60 Hertz. So I'm going to say we've got a 50 here, and then we choose a capacitor of 220 nanofarad, that is 10 to the power minus 9, like that. Now let's go ahead and calculate that. Now I'm not sure if you can see there, my calculator gave me an answer of 14,468 ohm. So that basically will mean it's 14.4, okay, kilo ohm. So that is the value of my capacitive reactance. So what it means is, what will be the value of my current? So the value of the current here will be just ohm law, okay? So which means I RMS, okay? I RMS here will be V RMS divided by XC, okay? Then V RMS in a case of 230 here, that will be 230 divided by the 14K, 14.4. Forgive my pen here is misbehaving. Okay, so that will be 230 divided by 14, okay? And I'm getting about 0.0 something there, so that will mean 15.9 milliamps, okay? Now you see I just rounded here because obviously you're going to find the closest resistor value. You won't find a 14K, you could find a 13K, or you could find a 15K. Either way, your current range is going to be from 12 milliamps up to 20 milliamps using the 220 nanofarad capacitor. So that will be the amount of current that's going to go through this Zener diode. So the Zener diode is safe, but not the inrush current when you first connect it. That's why we put a resistor here to limit the inrush current. Okay? Alright. Now, this is basically the circuit.